Recording. All right. Okay, and then I shall share screen here. Nice. Okay. That's connected. Any of the others who might have a question, go ahead and throw that into the chat. We'll do that when we come back. Or finish. I guess I don't mean come back. And then we'll get the question. Oh, all right. Next. All right, so number 9 from the practice test here says what? It says 2 very narrow, oh, I see what's coming up here. Yeah, narrow slits are 0.04 millimeters apart. A double convex lens made out of glass of beam index 1.6 and each having a radii of 50 centimeters is placed 20 centimeters from the slit. The screen is then placed 100 centimeters from the lens, okay? If light of wavelength 632.8 nanometers is projected through the 2 slits, how far up the screen is the first interference pattern? All right, there's some, I guess, big things and some little things here. Probably the first big thing, and maybe the most obvious, is this is a double slit. So d sine theta equals to m lambda. All right, so we've got a double slit here. However, what makes this one a little challenging is it also goes way back and kind of puts together this double slit and lenses in one problem, because what we have, and I guess I'll draw it here, is a double slit with a lens and then a screen. Now, this is kind of like in chapter 36, where we had multiple lenses, and I would say, okay, when you have more than one lens, take the first lens, and that lens will make an image. The image of the first one now becomes the object of the second. And I'm going to say the same thing here, but of course it's not 2 lenses, but it's kind of the same thing. In other words, the screen will be my, quote, second lens. My screen is the result of an interference that takes place, but it would be taking place from the image of the first lens. In other words, if I can say this well, is the whole idea of what we mean by an image is we're saying that after the light really comes from the object and goes through the lens, it has the appearance, it's been redirected, if you will, because of the lens, and it has the appearance of coming from the image of that. So I would say that the way to think about this problem is I'm going to get a double slit interference pattern. Okay, so I'm going to use this d sine theta equals an integer number of wavelengths. Okay, I'm going to use that for a double slit experiment. However, the double slit is actually the image from this lens. So I would, I guess, start this way and say, and maybe I'll draw maybe even a new picture down here. So here's the screen. Somewhere over here, and let's see if I can see some numbers here. I'm going to make a guess. We're kind of close to this lens here. And I know when we're close to a convex lens, the image then is bigger and further away. I don't know if that's going to be the case, but just kind of my beginning thinking is to say that I think the double slit coming to the screen is going to be, and maybe I'll put an I for image here. Well, we'll spell it out, image. Is the image from this one. And that's the thinking behind this problem. That's kind of the physics behind it.
Yeah, that was what stumped me, was like I was kind of confused as to whether, even though the slit's reflection would get bigger, I was unsure of like if we could look at it like the light was coming through this bigger slit with a different D.
Uh-huh. Yep. And so yeah, you're right. So it's going to be a different D, but it's also going to be a different location too. And so let's, I guess put in just our lens equation, 1 over P plus 1 over Q equals 1 over F, to figure out where even is this image. Where should we think about the double slit as it approaches the screen? And what I just said might be the hardest part of this problem, is just where do you begin? How do you even treat this thing? And so it is like a double lens problem where you have to say, okay, the second lens, this isn't really a lens, it's a screen, but the second optic, sometimes we like to call optical element, so we don't have to say lens or mirrors or screens, but the second optical element is getting its light from what would be the image of the optical element before it. So let me go back and just work with the first one. Of course, I'm kind of stuck. I can't really do this calculation without the focal length. So maybe another calculation I need to do is the Lensmaker equation. Find out, okay, what is the focal length? So that too is part of chapter 36 here. But I would have a 1.6 minus a 1. And they say it is a double convex. So, okay, so both have the same radius of curvature. And if I do it in meters, this would be a 0.5. This would be a 0.5. Now I'll need to watch my signs, if you will. Maybe I'll put the lens up here. Light coming in hits this one first, so that'll be R1. And R1 is got a center of curvature where the light goes, so it's a positive. But the second curvature right here is another 0.5, but it's actually a negative 0.5. Being careful with our sign convention. So this would be a 0.6, and this would be, let's see, 1 over 0.5 is a 2, and that would be a plus another 2. So that's a 4. 4 times 6 is 24. So 1 over the focal length is 2.4. And I suppose that's all I need. I don't really need the focal length, but I'll go ahead and figure out what the focal length is. So the focal length looks like it's 0.417 meters. Okay, so knowing that, I can come down to this line. 1 over the focal length is the 2.4. And I'd like to find out where the image is. And the object would be, how far is this object? And according to the words and the picture, looks like at 0.2. So we can get a Q here. Okay, so 2.4 minus a 0.2 reciprocated. Reciprocal of that gives me a negative 0.385. 3.85. Okay. So it did meet my guess that the focal length was more than the object distance. So if this is the position of the lens, then they're saying this distance back to the image is 0.385. And of course, a negative means it's on this side of the lens, the virtual side of the lens. And that was my guess. My guess was that this was kind of close and would be under the focal length, and that would make it over here. But I really didn't know that. It could have ended up over here. I just wanted to point out that I was just giving me something to work with in my picture, and now I'm just kind of confirming if I should still use this picture or redraw it. And it's like my guess is good here. And of course, the negative means what side of the lens it is. So there's where the image is. Now, I think this number was also given from the lens to the screen. The screen is 100 centimeters from the lens, so that's 1 meter. So the first part of this, which is to say, how far is it to the screen, I would add these two together. So this, as far as the screen is concerned, it appears to the screen, the second optical element, that the light is coming from this image, the double slit. And not the distance that would be 1.2 meters, but a distance that would be 1.385. Now, I'll keep going, and I'll keep that picture kind of handy, because the other part of this would be to say, now, what is the distance? I'll call it D2, I guess. Not to be confused with what I'll call the real separation, D1. But I tried to draw my picture because, again, I just know that if it is a virtual image and a convex lens, that it magnifies it. So whatever value here I had for D1, it's going to be bigger. And so D2, what I need to actually use for the screen, the distance D is a little bit bigger. Okay. So let me put in magnification. Magnification is minus Q over P. Let's see. So that would be the negative of a negative 385. And 0.2 was the distance of the object. So 0.385 divided by 0.2. And it looks like we've got a magnification factor of not quite 2. But of course, what we would be meaning by this is that the separation between the slits, D2, is bigger than the original separation, or you might even call the real separation, by that magnification factor. So D2 would be that magnification, which is almost 2, times the actual distance between them. So let's see, they say they are 0.04 millimeters. So this is going to be 0.077 millimeters now. All right. So that would be kind of the part that I would say would really, what makes this a hard problem is it has put together the double slit of chapter 37 and then the lens part of it of chapter 36. So I've done, I guess, the lens part of it. Now let's do the double slit, the D sine theta equals to an integer number wavelength. Where then, as far as the screen goes, the screen doesn't really know that there is a smaller set of slits and a lens. As far as the screen goes, it just knows where the light appears to come from. So the D in this equation would be the 0.077, and I'll put it times 10 to the minus 3 to put it in meters. So there's the D. The sine theta, we could write this since it says how far up. And so the light would be, hitting up here on the screen somewhere, call it y over L. And of course, this distance along the hypotenuse isn't quite L, but we like to say, look, if you're talking about a distance that's not far up, it's pretty close to L. So sine theta is really kind of the same as tangent theta, which is y over L. So we put a y over an L. And for this case, we've just said that the L would be the 1.385 meters. That's the distance from the image from the first one going all the way to the screen of the second one. And so that's what we don't know. That's what we're looking for. How far up? How far up is it? Now the M is which order, and it says first interference. So I'll just put a 1 there. And the wavelength doesn't change. The one before the break, it was kind of neat. We did change the wavelength because we put it under water, and some problem we did the last time. And now solve for y. Okay, so this is the 632.8 times 10 to the minus 9. Maybe I'll just bring the 1.385 over. I'll divide it by 0.077 times 10 to the negative 3. And this is 0.0, I'll call it 114 meters, which I guess would be 1.14 centimeters. And let's see if I scroll down. Don must have done this years ago. 1.14 centimeters. Good. So, I got the same number. Yay. Good. I still remember how to do these. All right. Pandemic hasn't taken all my brain power away yet. That and age. Yeah. I guess I'm still allowed to teach. Won't take away my license yet.
To teach, do you just have to pass a test or something?
No, not even that hard. They let anybody be a teacher. No, I should be a little more specific. When you go to teach community college, there really isn't a credentialing program like the K-12. So the K-12, there is to teach K-12, you have to pass some state tests, and then you also, to qualify, you also have to have a degree. And then let's see, how do they do that? And then there's a cutoff between elementary school and secondary school. So if you do middle school or high school, your degree has to have a be in that field. So you have to have a degree in math to teach math at the high school. But in elementary school, that's not the case. They have a more general requirement. Not sure on it completely. But the one I can answer best then is to teach at a community college. That you just must have a master's degree in that field. And then, and so like any job, that's the minimum requirement, but the truth is you'd have to interview. So that's kind of the test to see if you can be a good teacher is, you have to give a little teaching lesson, and which it's like any test, it's a nerve-wracking. You come in for the interview and you got to teach to a bunch of other professors and usually you're the young one, they're the old ones, and yeah, you're a nervous wreck going, oh, they know so much more than me and I got to teach this, and yeah.
Sounds like fun.
But
Yeah.
yeah, I suppose if nothing else, going through college and high school and learning how to, well, a lot of things. Part is learning to learn, but the other part is learning to face these challenges, like an interview or a test, and head on, and being able to function while you're nervous is maybe a more general.
And are you the head of your department?
Yeah, I guess I am now. We
So you've been the teacher that sits through a new interview every once in a while?
yeah. Well, yeah, I guess I've been here long enough now that I guess I have sat through everyone in our department who's I've hired with. There's one exception. You probably wouldn't come across her. She teaches just part-time. She teaches our general ed. It's our physical science program 103. She's actually been around longer than me, but everybody else, like Ron, I don't know if you.
Is that Amy Thompson by chance?
And then, well, Amy, no. Amy's not that old. She's younger than me. Person I'm talking to, she's in her 70s. So.
Oh, cool. Sorry.
Yeah. Well, and Lynn's her name. So. Yeah. But Lynn has been around. But no, Amy. Let's see. This Amy's 4th year. But.
Yeah, I think she teaches the tutoring stuff because she kind of led that when I was going through PAL tutoring training. So.
Yeah, right. Yeah. Now I have no connection to that. I have a connection just hiring her as a teacher, and then now that she's hired as a teacher, she has been heavily involved with that PAL tutoring stuff. I'm not very familiar with it, but if I'm even right, I think she's really just subbing in for the year for the person who's in charge is on sabbatical this year. So.
Why did you choose to teach community college instead of like university or high school?
Well, both of those are all very different. They're kind of a different door to get into. But I'll back it up one step, because really just getting into teaching was really not on my radar in the first place. So it was like, okay, I'm looking into teaching. I mean, I went to graduate school. I was never going to be a teacher. I did a little bit of teaching at the university, really because, I needed a job and an income to get through life. And so when I finished school, I started working for Boeing. And I was working for them. And then while I was working for them, a friend of mine who had gone to graduate school, who went into teaching and taught at the Pasadena City College, he contacted me, and he knew of the teaching I had done there, and he felt I was a good natural teacher, and he wanted to convince me to come teach one of their night classes. And at first I blew him off, and eventually he would work me down after a couple of years, and I go, okay. And then when I got to teaching it, I really liked it. And they had a special program. Besides physics, they had a special career photonics degree. It was kind of interesting. It helped feed the tech part of the aerospace community of Southern California. And it was really a neat program. And sadly, it was kind of drying up because I should also add that this was also the early 90s. And the early 90s is what they call the peace dividend. Communists fell. And we, from about 91, 92, I think when did they take down the wall? 89, 90. And Bill Clinton came into office in 92. And it just didn't seem like we needed a good, strong military. And a lot of the aerospace was cutting way back. And because of that, of course, they weren't hiring students. And of course, they weren't hiring new tech students out of Pasadena City College. No students were signing up for the program. So I kind of taught a little bit on the side, and the guy who ran it decided to retire. And I was actually thinking, well, they'll reinitiate it and maybe I'll apply for that job. And then they, in 95, decided to can it all together. And anyways, so I was kind of curious. And so I looked around and said, well, what other community colleges are happening? And there was a couple of openings across the state. One of them was at Santa Barbara City College. So, and then I got to looking into City College at Santa Barbara. I didn't know what a great school it was. And I was just like, hey, this is fantastic. And so, anyways, and then, so.
Was it the beach living that got you?
Yeah, there you go. Part of it, yeah. Yeah, actually the biggest put off was the high cost. I was like, oh, never be able to afford that.
It's cheaper, and I have a like 2004 Ford Ranger with like all my tools in the back, so not the most fuel efficient thing, but it's still cheaper for me to drive an hour to from Lompoc than to live in Santa Barbara.
Yeah. So So as a side note, I was even offered the job, and I was like, and my dean at the time who called me, I think I kind of burst his bubble a little bit because he was like all excited. He's like, hey, we picked you. We want you to come work. And I was like, can I have 24 hours to think about it? I'm not sure I can afford Santa Barbara. If that's the thing I want to do, I don't know anybody. It was such a big change. So glad I did it. But at the time, it was a hard decision. But everything in my life changed at that point. I changed my career. My wife quit hers and stayed at home. We had a son born that year. We moved to a place we knew nobody. Then we couldn't find any housing. That was really bad. We tried to find housing in Santa Barbara, just a place to rent, and we had so much trouble. One day it was our second day, and we just threw our hands up and said, well, let's go home. We started driving towards LA, and we got off in Ventura to get something to eat, and grabbed a paper and found a couple places to rent. And it was totally different rental environment. Because I was in Santa Barbara. I'd call the guy and say, hey, we're looking for a place to rent. And he goes, okay, I'm showing it at 4:00 today. Well, okay, I teach a lab. I won't be able to get off till 5. He goes, it'll be rented by 5. Either come at 4 if you want it, or don't come. I was like, but and then when I got to Ventura and called, the guy was just like, oh, where are you? Oh, yeah. I go, well, what time works for you? If you're eating, that's fine. I'll meet you at 6, 6:30, 7, 8, whatever works for you. I was like, oh, wow, that would be great. Because by that time I had already started driving, and I had 130 miles one-way drive up from LA to Santa Barbara. And I was like, okay, we got to find a place here. This is just too much of a drive in one day. That was 260 miles.
Yeah, that's a lot to commute for an everyday
Oh, yeah,
job.
every day. Well, and it was so much. So I got a hotel every Wednesday night. I'd get a hotel. So I would
That I mean, that on its own would add up too.
yeah. So that was adding up to cost too. Yeah. Ended up actually, the other side part of that is I ended up losing my great car. Back in those days, I had a GMC Jimmy. Loved the truck, but way too much of a gas mileage. My wife drove a little Toyota Corolla. So I go, okay, well, I'm driving this far. We need something with over 30 miles to the gallon. So I took the little Corolla every day. And then our son was born. So that became the family car, the big car, nice and safe. Put the car seat, the back seat. And so I lost that car. Wasn't until 2 years ago I finally was able to replace it with a truck. So now I got a truck. I was like, okay, good.
What kind of truck do you have?
GMC Canyon.
Okay.
It's not the big ones. Again, I got to drive from Ventura. So I was putting off a truck because I was like, man, I don't want to pay that price. But in that year, what took me over the edge, besides the fact that my other car was now 13 years old and having troubles a lot, I was that model. They came out with it's got an 8-speed transmission and can tow 7,000 pounds. And I got a 5,000-pound trailer. So
Worked.
the family car pulls that. So now our current family car is the a Yukon, but it's getting old too. It's a 2003. And so like, okay, what do we do? Our kids are older. We don't really need a big family car, but we still got the trailer. I can't buy a big V8. I can't drive all that to Santa Barbara. Anyways, that was a perfect blend because it's a V6 and it can pull 7,000. And it's like, okay, I'm there. So I'm only getting 24 miles a gallon up to Santa Barbara, but that's still pretty good.
Yeah, and I mean it's always useful for at least one family member to have a truck.
Yeah. It's amazing how many friends I have now that have a truck, right? Hey, buddy, we just picked up a washing machine at Lowe's and it doesn't really fit on the top of our Corolla. Can you help us get it home?
Yeah, ever since my dad bought his truck, he's been getting calls like that too.
So I like it. I said gladly. And my favorite type of pizza is so we'll move it and then have a pizza party. Okay.
I need to remember that next time someone asks me to help them move.
Yeah.
It's
Well,
always
the tradition really is my favorite beer, but I don't drink beers, so I don't have that answer. But I love pizza.
Good choice.
Pizza's definitely better than beer.
Yeah, I agree. New York style pizza too. That's my favorite.
Mm-hmm.
Yeah, yeah.
Well, Ryan, I don't know if I really answered it, but so I really got into community college that way, and teaching at the university is really kind of interesting. I don't think they do a real good job teaching. They do more research. I hope you don't have a negative experience when you transfer, but a lot of students sadly do. It's like they get to the university and it's just it seems like their focus on the quality of teaching is kind of on the low side. So
yeah, it's a lot less in depth too, like at least with the UCs because they're on the quarter system. So like imagine doing like 122 in 9 weeks. Like that's awful.
Yeah, my friend is at UCSB right now, and he's basically doing like this course. Like I looked at his syllabus; it's basically the same material, and his professor is a Dutch-speaking researcher who his English is his second language and he doesn't know it very well. And the captions for it too are done terribly. So he's like lost. I'm like, that sucks, man.
Hard science course and stuff if English is someone's second language, because there's a lot of very difficult words that you wouldn't use in everyday that like he doesn't know how to say in English. It'd be, I guess.
Mm-hmm.
Yeah.
Tough.
Yeah, and as a student myself, I ran into that. I had because there are a lot of visiting professors, and I remember one of the hardest ones for me to understand. I had a Russian visiting professor, and it was, I don't know, like 3 weeks before I finally figured out he was trying to say vector, not vector, or something to that effect. And I was, oh, okay, that's what he's saying. So that was hard. But I actually, and with that said, I do think universities have focused a little more on the teaching and the attention to teaching than they have in the past. So
Yeah, I've noticed a lot. I mean, like the big ones, you're still going to run into this, but like just touring schools, I've noticed that the like huge giant auditoriums that sit like 300 people are kind of becoming a thing of the past. Like most classrooms are at the biggest, like the physics room, from just like walking around campuses nowadays. And
yeah. So very different world. Yeah, no one of this. I mean, I was in some classes with 500 students. Big old auditorium.
It just doesn't sound ideal, like at all.
That just sounds like I mean, that sounds like those things you go to for fun, like like a lecture of 500 people. But I mean, I could not imagine grading that many papers.
Well, and then while you're pointing out, they do things very different, just a different thinking. But 30 years ago, I'd be in a classroom, big old auditorium, 500 people. That's the biggest, but 200, 250 was common. And it'd be a history class, and so you're listening to a lecture, taking notes. There's really no question answer. But to give them credit, you would do that either 2 or 3 times a week, and then there would be one time a week where they would break you into small discussion groups. So you would be in a group of 30, and you would go and have a discussion, and they called it the discussion section. And you would talk about the ideas, but it wouldn't be the professor, it would be a graduate student. So, but presumably that's where you had your more chance to ask questions and your more dialogue. So anyways, I hope I didn't waste too much time there. All right, so let's see. Let's go back to Hunter. You put one up here for me. All right, so let's
I'm asking 20 questions today.
Chapter 38, number 59. 38.
It was one of the ones that you separately in an email.
That I did what?
You sent separately in an email. You said that they weren't attached. So.
Oh, I did? Okay,
yeah.
Good. I'm glad you say that, because I need to grab that. And actually, I have the book open here. Maybe I'll just grab the book and go to 59. Oh, yes. Here we go. Maybe I'll just read it. I don't have a place to read it and do my work in my Zoom laptop here. Okay, so suppose that a single slit, okay, and so we got a single slit It is 6 centimeters wide, and it is in front of a microwave source operating at 7.5 gigahertz. All right. So let me kind of just make a picture of a single opening. Maybe I'll put a screen over here. I kind of like this problem in the sense that, did you notice they said microwaves, and we are dealing with a chapter really on, I should write down the time. What time we start this? 11. No, 1:11. There we go. But we are dealing with optics. And so one of the things that I liked about this problem, it was to realize that everything we've done about diffraction had to do with waves. So it doesn't really matter what the frequency is, even though if we're emphasizing optics, this could be other parts of the electromagnetic spectrum. In fact, in addition to that, this could be any waves. So these could be sound waves. And so sound waves would spread out. And so water waves, this could be the opening of a harbor, and the waves would come in and spread out. That's why, you know, even when you park a boat off to the side of the harbor, if the waves come in, you know, you'll see them spread out, and there'll be boats over here.
I think you froze for the first time. So.
That'll get, oh.
Bummer. Hey, at least we made it like halfway through the second session.
Yeah, it didn't freeze at all on the other one.
Yeah, today has definitely been your best camera day so far.
Yeah. All right, well, let's see if it'll be nice to us.
Now that we've said that.
Yeah, I better go knock on some wood here somewhere, huh? Okay, let me reconnect. But while this is connecting, I was trying to say here that one of the neat things about this problem is it helps emphasize that it is more than just optics. It's true for all of our waves. All right. So here we have the first part of this where they give us the frequency. So maybe I'll take a moment and then calculate the wavelength. So this is 3 times 10 to the 8th, and the frequency is 7.5 giga is 10 to the 9th. And so this will give me a number for the wavelength. So 3 times 10 to the 8th, then divided by 7.5 times 10 to the 9th, and we're looking at 0.04 meters. All right, so there's the wavelength to work with. And since I started halfway down that page, I didn't get very far before I need a new page. Maybe I'll put the page 1 here, I'll just put the wavelength. We'll see if we need the picture here. But now I can actually read the question, and it says, hey, calculate the angle subtained by the first minimum in the diffraction pattern. And so I haven't got a chance to say it today, but this equation, A sine theta equaling m lambda, is actually a little different, and an important difference between D sine theta equals m lambda. They look so much alike, which is a reason I think students probably confuse them. The obvious difference is the A and the D. So the D represents the distance between 2 slits. This equation was good for 2 slits or even multiple slits. So like the diffraction gradient was a problem we did earlier on. All right. But the big thing is right here that not only is it multiple slits, but this is the equation for the locations or the angle of the maximums, whereas this equation is minimums. And it's only valid for the single slit. And so the A is the width of the single slit. So kind of coming back to this picture, this opening is A, which they said in the problem was 6 centimeters, which I'll write as 0.06 meters. So that's probably the biggest difference in these two equations. One is used for maximums, and the other one is used for minimums. Now, that's fine. This is exactly then the equation I want because the problem said minimums. Now, another little subtlety is while I'm here is this equation is only valid for m equaling, and I guess it's plus or minus 1, plus or minus 2, plus or minus 3. But notice I didn't put a 0. Whereas the double slit equation was valid for 0 as well as all the plus and minus integers. So there's some very important differences here. And because, again, they're different, one is used for a single slit, one is used for the double slit. But just because they look a lot, they really are messed up and done, backwards from the, make sense. And students are trying to learn it, they can get those backwards really easily. Okay, so this is the equation I'm going to use. And like I said, it'd be true for any waves, whether they be sound waves, water waves, or electromagnetic waves anywhere in the spectrum. And so we just happen to be at the microwave region. So with that in mind, I can put in my A as 0.06 meters. Let's see, I need to come back to the question. Did they ask for the angle or the distance? It says calculate the angle sustained by the first minimum. All right, so we're going to go with angle here. Okay. So I'll just leave this as sine theta for the moment. Since they say it's the first minimum, the m would be 1. And the wavelength is why I earlier on went ahead and did the 0.04 meters to get the wavelength. And this is a little beyond the small angle for me. 0.04, 0.06, isn't that 2/3? Yeah. I'm in degrees. Maybe I'll leave it in degrees. So let me take the inverse sine of 2/3. And so we're looking at about 41.8 degrees. And good and bad. Microwaves tend to be big enough wavelengths that they tend to spread out quite a bit when they go through these holes. And that's actually really good, especially if you had like a building that, maybe has a lot of metal in it. The Wi-Fi, the phone signal, they can only come through the windows in the opening, but they spread out quite a bit. So all over in the side of the building, you can often pick up that signal. They don't just go straight through like sunlight. Sunlight, the wavelength is so small that you could tell where the sun is hitting directly and where it's not. And so you are either in the sun or not in the sun. But for your phone, you don't want that situation. You want to be you don't want to be able to pick up the phone signal anywhere you are, or a radio signal if anybody actually listens to the radio waves anymore and not the internet. but that's spreading out. And the same thing with sound. If somebody is in another room and they talk and they yell out the door, when it goes out their door, it's really nice that the wavelength of sound is so long that it spreads out. And so even though you can't visually see somebody, they can still hear you. It just spreads out. Whereas the visible light is such a narrow one, you can't see them directly, but the sound waves still get to them. They spread out so much. Anyway, that's kind of the secondary lesson here in this problem here. Anyway, so there's the first one, A. What is the relationship in the intensity? All right. Now, another part of the single slit was to say it's the intensity down the middle times sine squared of some phase angle beta over 2 divided by beta over 2 quantity squared. And that's probably the hardest mathematical one. I believe this is why the author decided to not mess with the single slit first, and then in terms of education, he went to the double slit. The double slit had a cosine squared, and he called it a phi over 2. But it didn't have this other effect here.
So that the sine squared beta over 2 all over beta over 2 squared, that's just for the single slit, right?
Yeah.
Okay,
So
cool.
this is the effect of a one slit, a single slit. This then is the effect of two slits. The overall is you got both of them together. Now, not for this problem. So I wanted to emphasize that. I'm going to cross this out because nowhere in this problem do I have a double slit. But I'm only pointing it out because in the last chapter, we actually did the double slit without this factor in it. We just had this, and we ignored this factor. And now this is probably the confusing part of his approach. Now we're asking you to throw it back in. Wait a minute, it wasn't there last chapter. Why do I put it in now? And well, the answer is we kind of ignored it. Just so that you can understand the double slit. And I think so, because the double slit is a little easier to understand because you only add up two waves. Whereas a single slit, you chop the opening into an infinite number of waves and add up an infinite number. So it's kind of hard for students to understand the single slit. So I think the author's approach has some validness in it, that he tries to get you to understand a double slit because it's a little easier than a single slit. But you can't really do a single slit without a double slit without a single slit, because every double slit has two single slits in it. and so when you throw this away and ask the students to add it back later, it's like, well, wait a minute, why didn't we have it last time? So that's probably the downside. Anyways, and that's more than this problem needs. I was just kind of pointing out that if this was a double slit problem, and I wanted to do it in its completeness, I would need both factors. But for us, it truly is only a single slit. So there is no cosine squared phi part to this problem. It truly is just a single slit. And this is where try to understand what beta is for this to make any sense. So beta, let me, if I can draw a single slit again. So here's maybe the screen. The beta is the phase angle. Let me go down the middle here. Between the ray that is the shortest length and a ray that is the longest. Because what is actually going on for the single slit is an interference of an infinite number of little ones. That's kind of the logic behind it. And so this is the result of adding up an infinite number. And then the beta is the phase from the first to the last. So that's kind of nice because once we get this answer, we don't have to worry about all the other ones. We just have to worry about how do we get the phase between the first and the last. So maybe I'll redraw it now that I added so many lines in here. So if this is down the middle, if the first is here and the last is here, and again, like we did for the double slit, if you draw across and make it so that the distance of this top one from where you drew across and the bottom one are the same, that little piece is the extra distance. And if the opening is A, then this makes a triangle, and you're looking at a leg where A is the hypotenuse of the right triangle. And so that is A sine theta, where theta is this physical angle down, which is the same as that angle in there. And then this is where you can either kind of memorize it, or for you guys, it is an open notes test. So you can just look up how beta is related to this physical distance. But I like to say the physical distance of A sine theta is to a whole wavelength, as beta is to one full cycle. So in terms of a wave, a full cycle is 2 pi. So if you bring the pi over, you get your beta over 2. So beta over 2 is this pi a sine theta over lambda. So if we put that into this equation, it becomes sine squared of pi a sine theta over lambda over pi a sine theta over lambda. And in some sense, maybe that's the equation to memorize. But when you have a sine within a sine, it's just not an easy equation to memorize. So I find it easier to remember it in terms of the phase between the first and the last piece, and then to work through what is the beta over 2 and then plug it in. But for you guys, if you see this on the exam, just know that that equation is actually in the book. Now, let me read the question again, because this is in terms of the angle. Sometimes we like to write this in terms of the distance on the screen. So keep in mind then that sine theta is that y over L. So we could do another substitution depending on the information given and replace the sine theta with y over L. And that is a little bit easier to memorize. But again, you guys won't be required to memorize it. And hopefully that will still serve you well for the future. So again, I got what I'll call all 3 forms here. And I need to read the question to see which form would be best. But I could write the intensity in terms of the phase between the first and last waves, or I can write it in terms of the angle towards the screen, or I can write it in terms of the position on the screen. And so these are all the same. And in mine, they say, what is it at 15 degrees? So it looks like this one here would be the appropriate one. All right, so let me bring that down here. And I'll even bring the I naught to the other side of the equation, because the problem said what is this ratio, the intensity compared to the center being the brightest. So how much has it gone down? And I'll go ahead and put in my 15 degrees before I punch in my numbers. I better double check. I think I'm still in degrees from earlier on, yeah. All right, so let's see if I can do these numbers. And I guess I need to come back to my picture then. Do we know the wavelength of this one? Yeah, we calculated the wavelength. Okay, do we know the A? Yeah, we know the A. Yeah, it looks like we know everything there. So let me do this number. This would be the pi. The A would be the 0.06. We would then have sine of 15 degrees. And we would divide it by a wavelength, we said, would be 0.04. Enter. So 1.22 really is that number. That's really the beta over 2. Now, this could be confusing to the student because I needed to calculate this in degrees, but now that I have it as a number, I need to do the sine of it, but that would be in radians. So this part right here is asking me to do the sine of that number in radians mode. So let me switch to radians. And I know it's radians because, you know, the meters cancels with meters. There's no units here. So this top, let me forget the square for a moment. In fact, let me write it this way. I'll just put the square on the outside. So this would be the sine of that last answer divided by the last answer. If I hit enter and then square that, I get a 0.593 for that intensity. There might be more to this, but I think I'm going to check the answers here. I need to go back from the practice test, and this is chapter 38, right? Number 59. So 38, scroll down to 59. And while I'm here, I might as well check A. So A, 41.8. Okay, good. That agrees. And then B, they got 0.593. Good. And so did I. Okay. So that's the intensity. Oh, and I don't like the way the author used the phi in there, because he does not mean in his solutions that phi is the same as the phi when he did the double slit. He used the symbol phi during the double slit. This is not even a double slit problem. So I'm not sure his choice of an angle was wise, but that aside, everything's done right. He maybe should have used some other symbol for the angle because the phi has kind of been used. Maybe he should have done an alpha or a gamma. Some Greek letter. We like Greek letters, but theta, a phi or a theta is already being really used a lot in the optics. So I wouldn't use it again. And lambda is a Greek letter, but is used for wavelengths. I wouldn't use it for an angle. And pi, I wouldn't use that for an angle because that's used for pi.
Yeah, I like omega and gamma. Those are always nice. Look cool.
Yeah. So gamma would have, I think, been a good choice. Anyways, I don't know if you're looking at the solutions, but that can be confusing in the solutions. And so I would prefer if you called that beta over 2. Okay, but then we can go on to C. And then C says, assume two such sources, are separated laterally by 20 centimeters and are behind the slit. What must be the maximum distance between the plane of the source and the slit if the diffraction patterns are to be resolved? Okay, so as a quick review lecture, the downside of light spreading out, I think I talked about some of the good side, like sound waves spreading out and your radio waves for your phone when you're in a building spreading out. So those are good things. But one of the bad things about spreading out is if you have two sources, so let me call this source S1 and another source of waves, number 2. See, if they didn't spread out, you would get like this pattern on your screen, or more realistic, instead of a screen, your CCD array of your camera. So you're taking a picture of it. And you would definitely be able to then detect that there are two little blobs of light and therefore two different sources. But if it spreads out, this light here may spread out, making a wider blob, and source number 2 may spread out, making a wider blob. And they get blurry. And if they blur together, you can't actually tell that you have two sources. So we call this the resolving limit. Now, you can have other resolving issues with your optical equipment. So this condition is the Rayleigh Criterion. And so the Rayleigh Criterion basically says that you would be able to tell that these spread out if the minimum from one of them right here, that's how I tried to draw it here, is at the same location as the maximum of the other. So if these blobs are spread out enough, you would just be able to tell that there's two blobs. You get them any closer than that, you really can't tell. What makes that nice then is that where the minimum is actually this equation, A sine theta. And I'll put the M at first, but if you're talking about the first one, then that's just a lambda. So the Rayleigh criteria is this, that this, if you have a given wavelength and a given A, then this angle is as close as they could be. All right, so, and still tell that they're two different things. So if I use that in this problem, I have sine theta, and I'm not sure I need to recalculate that. Isn't it the same calculation as part A? Because wasn't part A to find the angle of the first minimum? Calculate the angle sustained by the first one. Yeah, all right. So without bothering to have to recalculate it, although I guess I could, it would just be lambda over A, and lambda is 0.04 and A is 0.06. We would get an angle of 41.8 degrees. So these two things need to be separated by 41.8 degrees. If they are any closer than that, these microwaves are going to blur together.
And you won't be able to tell that there's two sources there. Okay,
Yeah,
cool.
yeah.
Yeah, I had a hard time. I had a little bit of a hard time understanding the conceptual part in part C, specifically that. So
Yeah.
Could you
Okay,
slide
now-
the paper over slightly to the left? Yeah, awesome. Thank you.
Okay. Now, calculator, I don't think I'm quite done. I found the angle, but I think they wanted the distance. So I got a little geometry I need to do. Let me just read it again. It says, assume that the two sources are separated laterally by 20 centimeters behind the slits. What must be the maximum distance the plane of the source? So they're saying that this separation is 20 centimeters. I'm going to put it as 0.2. In fact, I'm going to draw me a new picture here. So here's source 1. Here's source 2. Here's the little opening that the microwaves are going to come in and then diffract around and blur together. But they're saying, what is this distance from here to here? Let me call it X, just because I don't want to use D for distance, since we use that for double slit. I don't want to use L, because we often use L from the slit to the screen. So X is my choice. Okay, so call that X. So out to here would be X, and then up to the first one would be half the distance, so 0.1 meters, because down to the other one would be another 0.1 meters. And then if I make a triangle out of this, this would be that 41.8 cut in half. So 41.8 cut in half is 20.9 degrees. All right, so now I can do tangents of 20.9 degrees equals 0.1 over this X. So X would be 0.1 divided by tangent of 20.9 degrees. And I think I'm in radians. So let me come back and change it to degrees. This is an interesting problem because I did the first calculation in degrees, the second one in radians, and now a third one back to degrees. And got to watch then what the information is. Usually when you know, it stays the same throughout a given problem, but that's not the case here.
yeah, I'd probably lose points.
Gonna mess it up somewhere, huh? All right, so divided by tangent of 20.9. And looks like 0.26. So, and let's see, we're in meters. So if that distance from these sources is further away than 26.2 meters or 26.2 centimeters, 26.2 centimeters, then this angle between them would be under that Rayleigh Criterion. And they would blur together, which isn't very far. So seems like wouldn't make much to blur them together. And then let me check the answer. Oh yeah, and they got the same answer. That's interesting. They used cotangent. Huh. And they kind of did the same thing. They did it in degrees, but problem B they ended up doing in radians. Actually, the first part of B they did in degrees, and then they did the second part in radians. And then and then the first part was in degrees. So yeah, that's a recipe for mixing one of those up.
Yeah. Yeah, that was awesome though. Thank you.
Oh, good.
Went over a lot of good topics to review. So
All right, that's good one there. Okay, so let me juice that down and see if anybody, nothing more into the chat room.
I'm gonna head out, but I'll be back at 3. So
Okay.
thanks, Mike. See ya.
All right. Bye now.
Yeah, I'll be back too. My parents just got home, so I'm gonna help them unload their car.
Okay. Good for you.
All right. See you in a bit.
Can you teach my kids that?
All right. Bye.
Bye. Let's see. Well, we normally take a break at 2. We're close to that. So, you want to ask a question, Johnny, or should we just break a little early and come back at 3?
Yeah, I guess we could just break now then.
Okay.
Cool.
All right. Take
Okay.
care. We'll see you at 3 if you're back here.
Awesome. Thank you so much.
All right. Bye.
Bye.